Welcome to today's seminar. Today's speaker is Michal Opler, who will be talking about the hierarchy of hereditary sorting operators.
Thank you. So this is joint work with Vít Jelínek and Jakub Pekarek from Charles University. So let's talk about what we are going to be talking about. We consider a very general model of sorting, where at the input we get a permutation of some permutation, and then one sorting step is just an arbitrary reordering of the permutation, with like some of the reorderings allowed and some not, and that's modeled by the sorting operator to be just some set of allowed permutations that you can compose the input with. So you take the input and compose it with some permutation sigma, and then again you'd select some permutation from the sorting operator and compose the result of the previous. And the important thing is the sorting operator is not for one fixed length, but it's rather for all lengths. So it's an infinite set of permutations that should be able to sort any input sequence of any length. And the crucial question is, well, if I give you some sorting operator, just a set of allowed permutations you're allowed to compose with the input, then how many steps do I need to sort any input? So how it depends on the structure of the sorting operator. So it's a very high level overview, but I'll get into the formal definition. But first, the composing of permutations. So some of you probably seen this slide in some variations. So for us, permutation, it's a bijection. Permutation of size n is bijection of the set 1 up to n to itself. And we often write it out as a sequence of its functional values. So that's the images pi 1 up to pi n. And by this S of n, we denote the set of all permutations of size n. And a very useful way to thinking about permutations often is more geometrical rather than mappings or one-line sequences. And that's the permutation diagram, where we just take the permutation and sort of plot it out as points in a plane. So this would be a permutation 3, 2, 4, but sorry, 3, 1, 4, 2. It's on the x-axis we have the I, and on the y-axis we have the functional value of I. And it's actually useful even for the sorting to look at this permutation diagram, because if you then think of composing a permutation 2, 4, 1, 3 with this sigma, you can imagine it as writing this permutation 2, 4, 1, 3 to the left of the diagram, and then just tracking each element by this L shape through the point. And down there you get a composition of pi with sigma. So you can really imagine what happens when you're composing with the permutation by looking at the permutation diagram. It tells you how the elements travel throughout. So we'll come back to this many times, so it's important that you understand this. Okay, and if we allowed any arbitrary sorting operators, any set of permutations, then we would not be able to say pretty much anything, because you could, kind of select whatever you want, whatever you don't want. But we consider a hereditary sorting operators, meaning that the sets of permutations are closed under taking subpermutations. And what does it mean to be contained as a subpermutation? So we say that pi contains another permutation tau if we can find a subsequence of pi of the same length as sigma in the same relative order. So the red dots cannot be seen too much, but these 3 are red. And this is some larger permutation. It's 4, 2, 1, 3, 6, 5. And these 3 dots is an occurrence of 2, 1, 3. So you kind of standardize when you take just a subset of these elements. And
sorry, can I ask you something?
Yeah.
They're all on different sizes of sets. So pi is on a set different from a different.
Yeah, pi is of length n, and sigma is of length k. Right. The n probably should be there as well. Okay. And so we only consider sorting operators, the allowed permutations that are closed under taking subpermutations. But I would argue that it's a very natural restriction, because if you think about this, thinking about the composition as sort of taking the elements and tracking it through the permutation, then this essentially means that if something is in your sorting operator and you delete some of the dots, then this is still a valid operation that you can do. You kind of use only a subset of the dots for the sorting step. So that's why it's somehow pretty natural to consider that, to impose this additional restriction. Okay. Oh, and now a very technical definition, but it should not scare you off. It's actually fairly easy, but it will be used throughout. So a very natural way to define nicely structured and behaved permutation classes is to build them sort of from these arrays of smaller and simpler classes. So whenever I give you a matrix of permutation classes, K times L matrix, then it defines a class of permutations that can be cut up into K times L array, such that each cell contains a permutation from the given class. So if I give you this permutation matrix, and throughout the talk, I'll be using these shorthands for the class of increasing and decreasing permutations. And this bullet point is that it's a class of the singleton permutations. It's only one element thing. So, and this large permutation belongs to the grid class of this, if I take this kind of gridding. So I cut it up into 4 columns and 3 rows. And if you check, then each cell contains the permutation from the corresponding class. So the top left is an increasing sequence, the top right is an increasing sequence, this one is a decreasing sequence, in the bottom left there is a point, and then some of them are empty, even though they can contain something. But whenever I can cut up the permutation diagram into the K times L array, such that each cell contains a thing from that class, then that permutation belongs to that grid class. But it's often more useful to think about it in the other way, sort of, I give you this recipe how to build the permutations from that grid class. So you start with this 4 times 3 array, and then you fill in increasing, decreasing sequences as you like, and however you do it, it'll be permutation from that class. Okay. And now finally, for the formal definition of the sorting, so just a bit of notation. If I have 2 permutation classes, then by this composition, I mean I just take any pair of permutations from A and B and compose them. And this is meant to have the k-fold composition of the same class. So I take a k-tuple of permutations from the same class and compose them together. And so for the fixed permutation class, the sorting operator, this C sorting time of a fixed permutation is just the smallest k, such that the inverse of pi belongs to this k-fold composition. Right? It means that I can obtain the inverse of pi by composing k permutations from that class. And if I then apply this to the original permutation, I end up with identity because I'm applying the inverse of pi to pi. Or infinity if you cannot obtain the inverse of pi. And then the worst case sorting time of the class, denoted by this WST, is just the maximum taken over all permutations of, it's a function of n, and it is the maximum of these sorting times over all permutations of size n. So I'm essentially asking how many compositions with the given class I need to obtain any permutation of length n. Okay, so now it's time for some examples. So now it's kind of the time part where you practice like what does it mean to compose with permutations in these classes. So for this class, what happens if I compose a permutation with the permutation from this class? Can you tell? Like imagine this elements going from the left and then leaving in the bottom. No, if you imagine the elements going from the left and then leaving in the bottom, that means that you just split the input sequence into 2 parts and exchange them. So this is like a cyclic rotation and clearly that cannot sort. Like you cannot sort by applying cyclic rotations of the input. So slightly more interesting, what is this one where I have this increasing then 2 dots here and increasing?
It doesn't sort.
Sorry?
This doesn't sort either.
This does. Yes, it's like adjacent transposition. It allows you to, if you imagine going from the elements from the left, and there's going to be prefix that goes directly and suffix that goes directly, and then two elements that swap their order. So this one can sort and can sort in quadratic time. Because bubble sort, yeah.
Oh, you can make that on the left bottom.
Yes, and yeah, it's just a permutation class that's closed downward, meaning it can always be empty. Yeah. Yeah. What is this one? It's a fun one. What does it do to the input sequence? No. Exactly, that's pancake sorting. So it takes the input sequence, splits it into half, and then reverses the first half. So the motivation is that you have a stack of pancakes that you want to sort by their size, and the only thing you can do is put your spatula in there and flip some like sequence from the top. And that's exactly like reversing and prefix. So this is linear. This is actually the only academic paper of Bill Gates that proved this linear upper bound. Okay, so this is only a more involved version of that same. Like this is a subclass of this. But the reason I'm putting it here because this means you can take any consecutive part of the sequence and reverse it in place, and that's studied very much in genome rearrangements under the name of block reversals. So it's studied thing, and it's also linear.
I'm confused here. So you're saying this sorts in ON, but what? Like any sequence of
Length n, yes.
Gets sorted in linear time.
Linear in many steps, yes.
No, not linear time.
Not linear time.
Linearly.
Many steps.
Applied.
Yeah, linearly many compositions.
It's not about time.
Yes. Time might be a bit misleading. Okay, so this is linear. This one, take a guess what that makes it. Yes. It takes one element and puts it in the front, and then shifts everything behind. Right. So that's also linear. And then one final that's more. Then one more that's more that's more involved. So can you guess what this does to the input permutation? What it actually models?
It's like quicksort.
Yes, kind of. But like you cannot do the recursion in the same way as you do in quicksort. So it's rather you take the input sequence and then some of the elements hit the first part and some of them hit the second. So you split them into two buckets while keeping their like being stable. So you can do log n rounds with these two buckets to sort anything, to like doing radix sort on the sort of digits of the. So this sorts in logarithm time. So you only need log n of compositions of this. So here we see. Sorry? Yeah.
The dimension changes.
No. Yeah, the dimension of the.
So
Yes.
I mean, you're not getting the same thing as sorted. You change the size of the output.
No.
Okay.
It has to be a permutation. It's a permutation.
Yeah.
So it's
But then like
But
you
you
just
just
split
split
into
in
sequences or like swap them?
Sorry.
It has,
Well,
that's
Like
a good
what
point.
what exactly does this do? That's the
Yeah.
question. So okay. Back to the picture. So if you imagine that, this means that you have. So you have like a blue increasing sequence in the first part, and the red increasing sequence in the second part, and then you think about this sorting as sort of having this input sequence written here. That means that it splits it into a blue part, which leaves first, and then having a red part that leaves that goes to the second. So it means that you're essentially two coloring the sequence and then unmerging the two colors.
Some sort of
Expanding our definition, what does diagonal mean? I think. The diagonal means you can have both, basically.
Indeed.
Interesting.
No, this is some sort of.
This is bucket sort with two buckets being stable
Maybe
essentially.
quick sort, right? No.
No, you can't really. I mean, you wouldn't be able to do the quick sort because then you would have to recurse on each of them separately. But you can do radix sort. You can sort of first split them according to the last digit being 0 or 1, and then the next to last, and because it's stable, it'll be in log n. You can think about this afterwards, or we can speak about this afterwards. I'll be very happy to. Okay, but so here we see different sorting times that are achievable by these classes. And what is our main and only result is actually this sort of hierarchy of this. So we proved that every permutation class falls into these 5 categories. So either it cannot sort at all, so we've seen the cyclic rotations, or it sorts in quadratically many steps. Those were, for instance, the parallel transpositions, or it's between square root of n and n. There's this pancake sort, or it's between log n and log square n, where there is this bucket sort, or this sort of radix sort, let's say, or it sorts in constant time, but only the class of all permutations sorts in constant time. This is the full picture, and we'll be coming back to it several times. So let us start with the infinite case. So the classes that cannot sort. So we've seen one example, and then if you take the reversal of it, it also cannot sort, right? You're still doing cyclic transpositions, but cyclic rotations, but on the top of that, you're reversing the whole thing. So that still won't help you sort anything. And it turns out that there is only one other essentially example of class that cannot sort, and that's class that we call KR fringe. And that means that you have some suffix that's of fixed length at most k, and prefix of fixed length and suffix of fixed length, constant length, and in between it's just increasing permutation. So it means that by composing with permutations from this class, you can sort of rearrange the constant size prefix and suffix arbitrarily, but you cannot do anything with the middle part. So that's the reason these classes cannot sort, and it's reversal also. And the full characterization of these classes that cannot sort is actually that it's if up to finitely many exceptions, the class is of these cyclic rotations and its reverses, or if it belongs to this KR fringe class for some constant k. And all the other classes can sort in finite time, and can sort anything with finitely many steps. And I mean, I'm not going to prove this, but this essentially follows very easily from previous results on composition closed classes of permutations. So that were studied, and it's not that hard to get it from there. So that was the cannot sort. Now the other extreme, the class with worst sorting time 1, and that's only all the permutations, because I claim that any proper permutation class, meaning it does not contain everything, then the worst sorting time is at least linear, at least logarithmic, and this is just a counting argument, because by Marcus and Tardos, any proper permutation class, there is some constant such that the class grows exponentially with this constant at most. So it's really a counting argument that if I take a k-tuple of these permutations, then I can get at most c to the k times n permutations in total. So if I take the worst sorting time, I should be able to obtain anything, which is n factorial total number of permutations. And in order to obtain this n factorial as c to the k times n, this implies that k has to be at least logarithmic. It's the only proof that actually fits on the slide, and it's very easy. Just a counting argument. This theorem essentially has been generalized in this twin with small classes thing, that anything with constant twin, bounded twin with any class of is small in this kind of exponential sense. Okay, so started 2 extremes. Now I'll very briefly consider these 2 cases that are kind of super, mainly from linear to infinity, so this gap mainly. For this, I need to introduce some more permutation classes. So if I take any two monotone classes, this increasing, decreasing, and then make the grid class by either putting them next to each other or one on top of the other, that's what we call a monotone juxtaposition. So we've seen the ones that were next to each other, but if I take something like this, then it's also a monotone juxtaposition. And second important class is what is called the Fibonacci class, and that it's the hereditary closure of this infinite sequence, meaning I have these layers of size 2 that go on and on and on, increasing. And the reason why this is called, can you guess the reason why this is called Fibonacci class? It's enumerated by Fibonacci numbers. If you think about it, any finite subpermutation of this is formed by the layers of size 1 or 2, and then the number of ways you can write up any number as a sort of 1 plus 2 plus 1, etc. It's exactly the Fibonacci number. Why is this class important? It has been studied before. It's the smallest exponential class of permutations. So it has been proved, I think, by Martin Klazar, that if you have any class of permutation that for some n contains less permutations than this, than the Fibonacci number, then it actually grows only polynomially. So this is like the smallest you can get, the smallest base of the exponent for the golden ratio. And observation is that both this Fibonacci class and these monotone juxtapositions, they can sort in better than linear time, or at worst linear time. So for the Fibonacci class, you have these sort of parallel adjacent transpositions, so you can kind of start bubble sort, and then after 2 steps start the second iteration of the bubbling. Think about it, because you can do arbitrarily many parallel adjacent transpositions in parallel, so that allows you to sort anything in linear time. And for these monotone juxtapositions, it's kind of similar to that argument with the bucket sort. It's just you have to kind of account for different things, but they can all sort in logarithmic time, so they're really fast. And what this means is that as long as your class does not contain a monotone juxtaposition or the Fibonacci class, or its reverse, as long as it contains one of those, then you can already sort in linear time. So all the classes that can sort in superlinear time, they cannot contain any of these. So, and the reason this is very useful is because there's a characterization of these classes by Homburger and Vetter, which says that if you don't contain these, then you must be a finite union of PEC classes, and PEC classes are the grid classes where every row and column contains at most one element, or exactly one element, and it's either empty, increasing, decreasing, or a bullet point. So if you think about what the PEC class means in terms of sorting, it means that you kind of cut the input sequence into constantly many parts, and then you just reorder them in some fixed way while reversing some of them in place. That's the kind of what the PEC class means in the sorting language. And anyway, since these classes can sort in linear time, then anything that sorts slower than in linear, it must be a finite, belongs to this theorem, and therefore is a finite union of PEC classes. And with this, you can prove this gap between linear and quadratic by simply sort of going into some case analysis, because the structure of the classes is very bounded at this point. So you kind of know that anything that's slower than linear has a very nice structure, and you just kind of do some case analysis and something not that interesting. I just wanted to show that anything that sorts slower than linear has a very particular simple structure. Okay, question to this? Okay, and so this leaves me with the final and most fun part of this theorem, and that's the gap between log squared and square root of n. So again, more permutation classes. So a direct sum of two permutations is just that I put one to the top and right of the other. And if I take a permutation class that its sums closure is just I take direct sum of finite number of elements of C. Just closed it under this operation. And the two classes that I need is the class of layered permutations, which is the sum closure of the decreasing sequences. So here on the left, it's composed of these blocks, each of them decreasing sequence. And then the class of what we call the parallel block transpositions, which is the sum closure of cyclic rotations. So here, each of the blocks is the permutation from this class of cyclic rotations, and I have this increasing sequence of blocks. So, quiz question: what does this do to a sequence when I compose it with this one? It's like a nice interpretation. Yes. It cuts the sequence into some consecutive and like arbitrary number of consecutive intervals and reverses each in place. And this one is similar. It cuts it up into again arbitrary many pieces, and then it swaps the even with the odd, and some of them might be empty. So you kind of do this. That's why I call it parallel block transpositions. That you kind of inside of each block you do this cyclic rotation. And independently of the other ones. And okay, so we call capital Chi, I believe, the set of permutation classes that are all the monotone juxtapositions, these things. And these classes, the layered permutations, their reverse, the parallel block transpositions, and their reverses. And any permutation class is Chi avoiding if it does not contain any class from there, and otherwise we say that it's Chi containing. And the first thing is that, and that's the whole theorem of the gap, is that this is exactly the characterization, that if your permutation class contains some of these classes, then it sorts in at most log square time. And if it avoids all of them, then it cannot sort faster than square root of n. This is the characterization. The easier part is the upper bound. So for the monotone juxtapositions, I already mentioned that they actually sort in log n steps. It's kind of like the bucket sort, but for these ones, it's kind of the inverse of that. But it doesn't matter. It's still similar. And for these layered permutations, I mean, it's a nice exercise, I think, to like come up with how to sort in log square steps when all you're allowed to do in single step is to reverse any number of intervals in place. The same for parallel block transpositions. It's just a nice simple exercise to come up with a sorting algorithm in log square steps. So, but the hard part is this. It's just sort of what happens when it avoids the Chi. And for this, we have two parts. First is a structural theorem for these classes. Okay, so this iota n will be just the increasing sequence of length n, and delta n is just the decreasing sequence of length n. And this characterization of any Chi-avoiding class says that there is some constant, depending on the class only, such that whenever someone gives me a permutation from that class, then from pi, then I can cut up the pi into k times k array, so a constant size. K, this is k. Moreover, each cell of this array either avoids an increasing sequence of length n or decreasing sequence of length a, and length k. Said differently, it means that every cell is either a union of k minus 1 increasing and k minus 1 decreasing sequences. So each cell is either constantly many increasing sequences taken their union or constantly many decreasing sequences. Moreover, for if the cell looks like constantly many increasing sequences, it contains only linearly many inversions. So it cannot be arbitrary permutation you obtain as a union of k sequences. It contains only linearly many inversions, and symmetrically for that. And then there's the third bullet point essentially says that the cells that share the same row or same column cannot be interleaved too much. That somehow they do not jump too much the values between these two. Not important for our case. No. So this is sort of the one part is the structural theorem of these Chi-avoiding classes. And then what we do with this is kind of take a very unexpected turn to Treewit. So all the parameter people here should be happy to hear about Treewit. So the tree width of permutations is just the tree width of an associated adjacency graph. In the adjacency graph, I just take the diagram and connect the points from left to right. That's the red dashed line path, and from bottom to up, that's the blue solid path. So it's a union of two paths on n vertices, and the tree width of the permutation is the tree width of this adjacency graph. And important for us is something proved by Helen Rabinovich, that there are permutations whose tree width is linear in their size, meaning there are permutations whose adjacency graphs are expanders. But we just need that their tree width is large. That's all. We don't need to know anything about how they look. Just there exist permutations with linear tree width. And the kind of unexpected way we prove this lower bound is that we turn to a topological argument with drawing graphs on surfaces, with bounding tree width of graphs via drawing them on surfaces. So for any t tuple of permutations, sigma 1, sigma t, we define sort of a graph that captures how the sorting looks like. So it's going to be a graph that's called sorting diagram, together with drawing in the plane, but not non-crossing drawing, just a drawing in the plane. And it's obtained by taking this t+1 times t+1 grid, putting increasing sequences on the diagonals, and then these permutations sigma 1 up to sigma t on the upper diagonal, where the neighboring cells share the same coordinates. So for 2, 4, 1, 3, 3, 2, 1, 4, 3, 4, 1, 2, I have here 2, 4, 1, 3, 3, 1, 2, 4, and 3, 4, 1, 2 here. So that's how I place the points in the plane. And then the edges, I connect every pair of points that shares the same x or y coordinate. And additionally, I connect by a path these points in the lower right and topmost left cells. So this is a graph I define for any t-tuple of permutations. And maybe you can see where I'm going with the fact that this somehow captures the sorting, because if I imagine, essentially it's an application of that sort of graphical composition over and over, right? I kind of put the sequence here and then get the first composition, and this main diagonal just copies the elements to the next sorting step. So every element travels throughout the composition on a separate path until it arrives in the final cell. So essentially, if I put here the sequence and track it through the sorting diagram, I'll obtain the composition of pi with these permutations. And okay, having this, the first thing is that the tree width of this graph is at least as large as the tree width of the adjacency graph of the permutation that it's sorting, right? Because if I take this and contract, sorry that I don't have time to define the sort of tree width and all these things with minors, but tree width is preserved under taking minors, meaning it's preserved under contracting edges. And so if I contract each of these monochromatic paths, like all edges on these monochromatic paths, then I end up with these two paths on n vertices, and one of them is going to connect them in the value order, sort of left to right, and the other one's going to connect them from the bottom to up. So you exactly obtain that adjacency graph of pi. So this graph has to have tree width at least as large as the tree width of the permutation it's sorting. And our goal is to show that the tree width of this graph cannot be too large. And by that, therefore we also upper bound we get the lower bound on the number of steps. Right, so we have this. And the sort of magic part is that taking our structural theorem, we can show that if we have the chi avoiding class, then we can draw this sorting diagram on a surface with small genus and not too many edge crossings. Particularly, we can draw it on a surface that has genus linear in the number of sorting steps and using roughly sorting steps times n edge crossings. It's just take this and kind of add sufficiently many handles and crosscaps at nice points. Like you essentially start with this drawing in plane, and then you help yourself with adding a small number of handles and crosscaps. And then you just throw in the large hammer from like structural graph theory that by Dumovich, Epstein, and Wood, not exactly in this formulation, but it's a very straightforward corollary of their results, is that any graph on n vertices that you can draw on surface of genus G with at most x edge crossings, then its tree width is this function, square root of G plus 1 times n plus x. And if we just, plug in the values we have, we'd get that the sorting diagram has tree width at most the number of sorting steps times square root of n. And because there are permutations with linear tree width, which you have to be able to sort, then to sort these permutations, the sorting diagram actually has to have at least square root of n steps, because otherwise its tree width would be too small. So that's the whole argument here. And yeah, then some conclusion. So obviously we don't know if these intervals are actually not smaller. In particular, for this one, I think we very much believe that there are only classes that have linear sorting times, but we couldn't improve the lower bound, and the current lower bound is pretty convoluted, like in the way it's obtained. So probably a very different technique is needed for that. But we do believe that it's only everything here is actually located at n. For the lower non-zero measure interval here, we're not so sure. Like our opinions differ in whether we believe that it's actually only a log n or larger. So for all the monotone juxtapositions, we know that they sit at this left end point. And for the layered permutations and the parallel block transpositions, we only have a upper bound of log square. But this is a very easy combinatorial question that I hope we've been saying it with BTEC on multiple venues, and nobody's been able to solve this. Because if you rephrase it, you're really asking, your sorting procedure is cutting up your input sequence into any number of blocks and reversing each of them in place. And how many sorting steps you need at worst, right? So we have an upper bound of log square n, we don't have a lower bound better than log n, and it seems like an easy, straightforward question that you don't need any sort of these hard grid classes and things to ask yourself, but we've been unable to obtain an answer to this. We'd be very happy to if someone did. Yeah, and that's all. Thank you.
Any questions? No questions?
So just to make sure, so your hereditariness in terms of what sorting permutation you're using, it means that the whole permutation has to be in your class. It's not like I take a small permutation and put identities on either side.
Yes.
That wouldn't.
Yeah, that would make it a bit different.
Yes.
But I mean, if you have a hereditary sorting operator, then what you obtain by allowing yourself this is still a hereditary sorting operator, which is a different one where for each permutation in your original class, you add these two increasing blocks in the corners.
Any other question? So let's end this video.